we're going to cover how to implement nonlinear model predictive control. And if you come to APMonitor.com/DO, you'll come to the dynamic optimization website, and then just on the right, scroll down all the way near to the bottom until you reach nonlinear control. And then at the bottom of this, there's going to be an exercise, and this is going to be our CSTR, and we're going to be adjusting this cooling jacket temperature to try to control the temperature in the reactor and minimize the concentration of A. Okay, so we have a reactor here with pure A coming in. We have an A to B reaction, just generic reactant and product, and we're going to try to control this exothermic reactor. Okay, so we also, a couple other pieces of information. The reactor temperature should never exceed 400 Kelvin, and then also the cooling jacket temperature can be adjusted between 250 and 300 Kelvin. Okay, there's more information about this problem. If you come to the process control side, you'll see developing this model in Simulink. There's a video there, and then also some more information about the parameters, about the variables, the equations, and so forth. Okay, and how to implement it in Simulink, linearize it, etc. So I'm going to come back here. There's a first example on how to implement proportional integral derivative control. That's kind of a basic type of control to implement the temperature control with cooling jacket temperature as a manipulated variable. There's also linear model predictive control. The one that we're going to cover right now is this nonlinear MPC. Okay, so go ahead and just download that archive. It's going to be the solution, or you can start with the files above if you want. I'm just going to walk through the solution though. So I'm going to extract it. Don't forget to extract it. It won't run quite right if you don't extract it. And then what I'm going to do is open up first of all this reactor model. So this is a model of my reactor. It has parameters, variables with initial conditions, and then just the two equations. There's actually some extra code here. This is just to put a graphic of the reactor onto the screen. So the only thing you need is from lines 45 and above. Okay, so there's our reactor. It's a nonlinear model. One of the things that's most nonlinear about it is that it has this exponential dependence on the inverse of the temperature, and that it makes it extremely nonlinear, especially for high temperatures. Okay, so the reaction will start increasing, and then we also have this exothermic term here, so that as the reaction starts going faster, we have more and more heat that's going to be generated, and the more heat that's generated, the reaction goes faster. Okay, so the reactor has a tendency to run away. It goes up to very high temperatures. So we want to try to control the temperature below 400 Kelvin while trying to minimize the concentration of A. So I'm going to go ahead and just open up this script. First of all, this is the model predictive control function, and what I'm going to do is just walk through some of the commands needed to set up the MPC controller. Everything's contained in this one script. Okay, so I'm just going to walk through it right here. I have some persistent variables. Those just stick around even when I leave the function. So when I come back again, I don't need to redefine them. So that's going to be valuable because I'm going to have a counter, for example, and just on the first cycle, iCount is not defined, so it's going to be empty, and it'll come into this initialization area. So everything from line 7 all the way down through to, okay, I'm still going here, all the way down through to 99. That's all that's required to initialize the controller, and there's just a couple commands, a couple sets of commands that we're going to have to go through to configure our manipulated variables, control variables, tune the controller, and then everything from 101 on down, that is actually what happens every cycle of the controller. So it skips all the way down to 101 after it's gone through the second time. Okay, so I have 4 inputs right here, U1 through U4, First one is my temperature set point. And then I'm also going to have some other inputs as well. Those are just going to be disturbances. And then also I'm going to implement a deadband for my set point. So it's going to be between an upper and lower limit. And then I'm going to input some of these measurements. These are going to be disturbances that are measured. Okay, the flow rate, Q, CAF, that's the concentration of the feed, and the temperature of the feed as well. Okay, so this next section right here, this is where I implement the set points. Okay, so if I use a squared error objective, I need to have just a set point. But if I use an L1 norm with a deadband, I need to define set point high and set point low. And then I solve the model predictive controller right here, and then just display the output. Okay, in this next section, I'm just retrieving the solution. I look to see if the status is good. That means it was successful. And if it's equal to 1 or good, then I retrieve the new values and also the temperature of the model and the concentration of the model, etc. Else, I'll go ahead and just flatline it. Okay, I'll just put in some values and you'll be able to see that it is bad. Okay, just on the first cycle, what we're going to do is turn on the controller, request control mode 3. That means it's the controller actions are going to be implemented, and then also open up a web viewer. Okay, so those are the steps for the controller every cycle. Let's back up and just go through some of the initialization steps. And I just want to do that when we run it in Simulink. Okay, so I'm going to go ahead and open this up in Simulink. CSTR nmpc.slx. That's the file that we're going to be running the model predictive controller with. Now in this case, I've just replaced the whole model that was there before with an MPC block. And the reason why I can do this is because I'm assuming no model mismatch. Okay, so model mismatch means if I have a difference between my model and measured values, then I'd have to set up two different blocks. But in this case, I'm able to use the nonlinear model predictive controller to both simulate and control the process. So I just replaced this orange block is a replacement of the CSTR model that was there formerly, and then I'm going to have 4 inputs, the first one being temperature, inlet flow, feed concentration, and then feed temperature. Okay, and then I'm going to have just 2 outputs. I'm going to have reactor temperature, and actually it's going to be 3 outputs. Okay, it looks like my control moves, or no, temperature, and then the second one, let's see, what are those? Let me come back into my controller and see what those 3 outputs are. Okay, so I'm going to come down to the bottom. Okay, so there are my outputs right here, Y1, Y2, and Y3. The first one is the cooling jacket temperature, and the second one is the temperature of the reactor, and then the concentration in the reactor as well. Okay, so let me go ahead and just make this a little bit bigger, and then what I'll do is go ahead and put just a breakpoint in here, and then run the Simulink controller. To put a breakpoint in, you just have to touch the side next to where you want to put a breakpoint, or I think there's a shortcut key as well, maybe F12. Okay, or you can put manage your breakpoints here at the top. Okay, so let me come back into the Simulink, and I'm just going to go ahead and run this for 5 minutes of simulation time. So it's going to go ahead and compile and then start running. And okay, so it hit this breakpoint right here. I'm just going to step through it. Okay, just hit the step button in the top. I'm going to load my APM library, specify a server, an application name. Okay, I'm going to clear any previous application by that name, and then load my reactor model file, and then also my time horizons. Reactor.csv contains the time horizon. I'm going to specify certain fixed values that I'm going to not try to estimate or change. Just I want to maybe see the web interface, the volume of the reactor, the density, the heat capacity. That is the delta heat of reaction. I also have a pre-exponential factor on my Arrhenius expression and a heat transfer coefficient. Okay, these are my manipulated variables. These are the ones that are going to be potentially changing over time. Really, I only needed to find the first one, TC as an MV. The other ones, I'm just going to have those as status off. Okay, so those are just going to be off for the duration. And then, but if I was able to control them, like the flow rate to the reactor, then I could have an additional control here to try to achieve different objectives. Okay, so I have just a state variable. That one's just for view only. And then a controlled variable, that's the one that I want to set up a set point and try to drive it to a target. Okay, I mode 6 is nonlinear control. And then I set up 3 nodes. Those are interpolating nodes in my orthogonal collocation on finite elements. And then I have control units and history units. That's just for display purposes on the plots. Those are going to be in minutes. Okay, and then controlled variable type 1, that's an L1 norm. 2 is actually squared error. And then maximum number of iterations, that's for my solver. I can use IPopt or APopt, for example. Okay, so let me go ahead and just keep stepping through this. History horizon, that's how many points I want to display in my plots. That's more of a web viewer configuration. Okay, tau, that is how fast I want it to reach the new set point. When I have tau equals 1, that means a time constant of 1 minute, or it'll get 63% of the way there within 1 minute. Status, that means it's on, and it'll include it in the objective function. I'm not measuring it. There's my upper limit. Now this one is actually kind of important for the solver. You saw that exponential function, it's a function of temperature. It's kind of interesting because without this statement right here, the temperature upper, without constraining that, then it has a harder time solving. And so sometimes when you put selective bounds on your optimization problem, it becomes just a little bit easier to solve. Okay, so now here is my temperature of my cooling jacket. I have an upper limit, that's 350. That's the amount that I can move it each cycle. I just tell it, move it only 10 degrees each cycle. Okay, also the cooling jacket temperature, it may not be able to physically be able to change that that fast anyway, so you might need to include a more restrictive Dmax to model how fast your manipulated variable can move. Okay, also a lower bound, 250. I'm going to turn it on, meaning that the optimizer can use it to try to improve the objective function, and then I'm not going to measure it. Okay, now here is my request control mode 1. That means I leave the controller off, and then I'm going to turn it on after the first solve. Okay, just initialize everything. Again, I'm going to have my web plots that are going to update every 3 seconds. Okay, initialize iCount, and then we've been through the rest of this. So I'd only need to go through up to line 99 just the first time, and in subsequent times it's just going to jump right to line 101. So I'm going to click continue now, and let's come back here to okay, so it opened up this dashboard. I'm actually going to copy this into Firefox instead. It looks just a little bit better now in Internet Explorer. Okay, so I'm going to come to my CVs tab, just click on, let me come over to Chrome then. Okay, it looks like I need to load the Flash player or something. Okay, so let me come over to Chrome, and let's just look at this temperature. Okay, so I'm going to try to drive it up to this new set point, and right now I'm going to go and close Firefox, and let me close this version of Internet Explorer. Okay, and then I'll come back into my Simulink. Okay, I'm going to click on temperature, and let's go ahead and see how this nonlinear model predictive controller does in terms of controlling the temperature. It looks like it's having a little bit of a hard time starting right here. Let me see what is going on from the So you can check it out here, how long it took to solve. Oh, you know what? I'm at a breakpoint right now. That's why. Okay, so it only took 0.016 seconds to solve, and you can see your objective function, and it took 3 iterations. Okay, the first cycle was 0 degrees of freedom because request control mode was off. Okay, so I'm going to come back here. Let me go ahead and just delete that breakpoint, and I'm going to come back and continue. Okay, click the continue button at the top, and come back over to temperature. Double click on that. Okay, so this is going to be the temperature plot. Okay, so it's going to try to start controlling to this new set point right here, 370. Okay, so it can also open up the concentration right here, and let me come into the web viewer to see this. Okay, so I think my internet connection might be running a little bit slow right now. Let me switch it over to another server. Okay, so I'll just go ahead and run it off of this laptop instead of connecting to the internet to do it. So I'm just going to change the server name. Okay, so if you have a version of the APMonitor server on your computer, you can change it. Okay, so I'm just going to compute locally. I'll change that to just my local host. Okay, and then I'll comment this one out. Okay, so let me go ahead and try that again. Let's go ahead and run. I'll go ahead and open up this Simulink function. Okay, and then we'll try it one more time. So this is going to try to run off of my tablet computer. Not a lot of CPU, but we'll go ahead and try it anyway. Okay, so let me run it starting here. Okay, again, that's not the best interface. I'll come over to Chrome and just put it here instead. Okay, so you can see a little graphic of the reactor come up. It's going to update the temperatures as we go. Okay, just a little animation that's going to pop up in the web viewer. Okay, and then the one of the things that we can look at. Let me come down here to temperature. Okay, so it's going to try to control the temperature by changing the this cooling jacket temperature. And so you can see it came up, and then just right at the right moment it dropped the temperature down to about 280 and then back up to 294. Okay, so you can see this progress right here, and then it comes back up. Now it was able to control the temperature up to a value, it's approaching about 270 right now, but the important thing is we were able to get the concentration down. In this case we want to get it down below 0.2. It was able to do that without spiking the temperature. Okay, so now in this case, this is different than the PID controller or the linear model predictive controller, because in this case it had an accurate representation of the system, and it didn't have that model mismatch that caused the temperature to spike. Okay, so here are the final results right here. You can see the in the top the temperature goes up and then down and then levels out. You can see the concentration levels out to about 0.2. If you want to get this down a little bit lower, you can just raise the temperature set point, and then the model predictive controller would come up to the new set point. It came up, our tau was 1. Okay, so that means we went about 63% of the way there in 1 minute. Okay, so that was a purposeful approach to the new set point. You could also try to increase the speed a little bit more or decrease it as well. Okay, so That concludes this demonstration. Again, just to summarize, what we've done is we implemented a nonlinear model predictive controller with a very nonlinear process, and because there's no difference between the model and the actual process, the simulated process in this case, we got excellent control results.